Alright, hey gang. Had a bit of free time, so I figured we'd give one of these competitions a shot. So before we get started, I just want to say today I'm going to be doing CodeJam 2017 1B, and there'll be a link in the description of the video. So if you are watching along, I would highly recommend giving it your own shot. Even if you're not going to get through any of the problems, just having a read through them and thinking about them yourselves is going to make watching me solve them a lot more useful. Alright, I think that's all I wanted to say, so I guess we can get started. C2 cruise control. Okay, so I'll give it a read and then I'll give it some time to think. So Annie is a bus driver with a high-stress job. She tried to unwind by going on a Caribbean cruise, but that also turned out to be stressful, so she has recently taken up horseback riding. Today, Annie is riding a horse to the east along a narrow one-way road that runs west to east. Okay, she's currently at kilometre 0 of the road, and her destination is at kilometre D kilometres along the road, and numbered from west to east. Okay. Yep. There are N other horses travelling east on the same road. All of them will go on travelling forever, and all of them are currently between Annie's horse and her destination. The ith of these horses is initially at kilometre KI and is travelling at its maximum speed of SI kilometres per hour. So let's just start off by drawing that, and then we can read the second half of the problem. So we've got a flat line from east to west. Let's just call this, what was it, Steed 2 cruise control. Steed 2 cruise control. Alright. So we've got a flat line from west to east. Right, we're somewhere in the middle at kilometre 0, so that's where we are. And we want to get to kilometre D. So I haven't seen any constraints that say D needs to be positive yet, but let's just assume it is for now. We need to get over to D, and then somewhere in between, there's all these little horses, H1, H2, and H3, and they're all moving at some speed, I believe. Sorry, I wasn't sharing that. Let me go on to OneNote and transition. So that was what I've just drawn there. So we've just got flat line, the red dot there is where we are, D might be the blue dot, and then in between we've got all those horses. Okay, let's go back to the problem statement. So the problem statement, we've got horses are very polite, and a horse H1 will not move ahead of another horse H2 that started off ahead of H1. Okay, so as soon as a horse is behind another horse, it will stay behind that horse, or at the same position, always. Yep. Every other horse other than Annie's travel at their maximum speeds, except that whenever a horse H1 catches up to another slower horse H2, they've reduced their speed. Okay. Annie's horse, on the other hand, does not have a maximum speed and can travel at any speed that Annie chooses, as long as it does not pass another horse. To ensure a smooth ride for her and her horse, Annie wants to choose a single constant cruise control speed for the entire trip. Okay. And we don't want to pass any horses along the way. So let's get the notes back up and we can draw the rest of that problem. So each of these horses have their own speeds, right? So H1 might move at, say, 5 kilometers per tick, right? A tick being a second or a minute in this case. H2 might be 3, and then H3 might be 4, right? And what that tells us is that, say, after one tick has passed, or 1 minute of time, we can update the horse's position to 5, 3, and 4 kilometers across in the positive direction, right? So H1 was here, but now we go 5 across, and we stop here. H2 was, say, here, and we go 3 across to stop here. H3 goes 4 across and stops here, right? So we've still got 1, 2, and 3 as the spots. And then I guess what it's saying is that the next tick, H1 is going to collide with H2, and so it's going to slow itself down in order to not pass H2. So at the next tick, it might look like H2 has moved 3 units across, and H3 has still moved 3 units across, but H1 has not gone the full 5 units, it's maybe gone like 4, so that it's coincidental with H1. Right, so now H1 and H2 can kind of be considered the same horse for the rest of the problem, because now they're both going to be at the same point and both moving at 3 kilometers a tick. Right, and what we need to do is decide on a single speed that we can move so that we never change our speed, and we also never go in front of a horse, right? We need to also be following those politeness rules. So that's a problem statement. Give it, pause the video and give it a minute to think about it. And now it's my turn to give it a shot. Okay, so I think the thing that we want to notice is that we kind of, in order to be behind all horses, we just need to be behind the slowest horse at any point in time, right? So for now, that is horse 1. They're the slowest, or the horse that we are the least behind at the moment, right? And provided that horse 1 never catches up with any of these other horses, right? Then all we need to do is calculate when horse 1 reaches this endpoint and say, well, that's going to be the slowest horse. In general, because the horses are always slowing down and not speeding up, all we actually need to compute is when the last horse, so when horse 1, I guess, gets to the stable, right? If, let's look at the horse's position over time, right? So let's say time is 0 here and it ends at some point t. And let's say on the y-axis here, we've got the distance from the end point. So 0 is when the horse has made it all the way to d, and let's just say a maximum of n. So if we draw the horse's position over time, we'll see that initially it goes quite fast, right? And then at some point, it might slow down because it collides with another horse. And then it might do the same thing, and so on. But the interesting thing to notice is that there's some concavity to this graph here, right? At no point do we speed up after we collide with the horse. We're always slowing down. And what that means is that, well, we can graph our position as, for example, the red here. I think actually I might have some issues, but let's say I'm here actually, that's fine. So if I'm above the horse, which essentially means I'm behind the horse to begin with, if I just draw a straight line on this graph to t, we can see because we're always slowing down and we've kind of got this downwards curve, we're never going to be intersecting the horse's path, right? So if I travel at a constant speed to get to the end at the same time as the final horse does, there's no possibility of me colliding with another horse, because for that to happen would essentially mean that we need to go fast at one point and then slow at another point. Am I drawing it the other way around? Sorry. Yeah. Sorry. So slow at one point and then fast at another point, I should be saying. Right, which is not in the rules of the polite horses. The polite horses will always start as fast as they can, and then they will lower that speed to follow the politeness rule. So what this graph is telling us is that all we need to do is calculate when the last horse gets to the end position D, right? And I'm guessing if we look at the bounds for this problem, that is not a particularly hard problem to solve. So we can see that even for the large data set, there's only n horses by the looks of it. Yes, n is the number of horses. So all we need to do is just calculate when the nth horse gets here. So let's go through some of the math for that for a second. So let me just figure out how to insert some space in here. Insert space would probably do the trick, I hope. There we go. Nice. Okay. So we've got our initial position. Well, actually, let's not even draw ourselves. We've just got a final horse, H1, and we've got some horses in front of it. Right? And I think what we want to start by doing is maybe work in the reverse direction. So if I can first figure out when horse H4 gets to the end, then it becomes a lot easier to calculate when horse H3 is going to get to the end. So for the final horse, the time it takes us to get to D is very easy, right? If H4 has some speed, S4, well, the time it takes is simply going to be the distance it takes, so say D minus H4, divided by the speed it takes, right? So these two. That's all we need. So the time for horse 4 is going to be equal to D minus H4 on S4. For H3, it's slightly different. So for H3, we need to calculate if it's going to collide with H4, and if so, when, and the time it takes to collide with H4, right? So let's assume that, well, yeah, we can calculate when they're going to collide first off. And essentially this is just some linear equation solving. So if we assume that H3 is going at max speed constantly, and its speed is like that, and the distance, so again I'm using the same graph where this is the distance from the endpoint, right, with some maximum n as our y-axis and the time as our x-axis, right? So this blue one at the top might be the position graph of H3 if they're not following the polite rules, whereas this might be the position graph of H4, right? So what we need to calculate is when they collide on the line, which is essentially saying at what point in time does this happen, right? So we can write out the formula for these two lines. For H3 it would be, well, the gradient is going to be rise over run, or distance traveled on, or just the speed, sorry. So S3 should be the gradient of that line, so S3 times x plus, and then our y displacement here is going to be our initial position, right? So plus H3. And I guess we want a negative S3 because we're going down and not up in our graph. Alright, so that might be our first line. Our second line for H4 is going to be negative S4x plus H4. That sounds right. Yes. Okay. And then we want to calculate when H3 hits H4 on this line. Now notice that it might be in the negative distances, in which case it's too far along in time for us to care. But we can solve for that. So we want to solve for x, I guess, which in this case is the time. So let's just quickly do that. So we get negative S3 x plus H3 is equal to negative S4x plus H4. We get S3 minus S4 x is equal to H3 minus H4, and then we get x is equal to H3 minus H4 on S3 minus S4. Oh God, I'm still sharing the screen. I'm sorry. I will get better at this, I'm sure. I'll go over what I just said. My apologies. So we were drawing the different horse positions, right? So we had H1 through to H4. We calculated how much time it was going to take H4 to get to D, which was this D minus H4 and S4 thing. And then we started calculating these two lines on the displacement graph I was talking about. So this one is the line for H3, this one is the line for H4, and at some point, provided H3 is moving faster than H4, they're going to intersect at this point, right? And to calculate that intersection point, we are just solving for this system of linear equations. So that's what I've got at the bottom here. So we find that x is equal to H3. Let me just write that a bit nicer. So x is equal to H3 minus H4 on S3 minus S4. So if x is less than however long it took us for H4 to get to D, then we know a collision occurs, right? Collision. And if a collision occurs, then the time taken is going to be longer, right? So let's just remember what was going on here. So yeah, if there's a collision, then we know that essentially H3 travels at S3 for x ticks or seconds or whatever you want to say. Right, H3 travels at S3 for x seconds, then it collides and travels at what am I saying? Then it collides and travels at S4. Sorry, got a bit of a mind blank. S4 second. S4 for how many seconds? Well, it'll be How long will it be? Well, it should just be it should just be minus h4 on s4 minus x seconds, right? So essentially what it's saying is because h3 and h4 will then get to d at the same time, we don't care that they've collided, more or less. So as soon as we have a collision, we know that h3 is going to take just as long to get to the station as h4 does. So essentially, if there is a collision, we don't care, because it just means that the horses are going to kind of collide and then combine, and then the slowest of the two is just going to tell you how long it takes you to get to the end. So we don't even need to calculate these collision things. All we actually need to do is figure out who is going to be the slowest, assuming that there are no collisions at all, right? So let me just insert some space and we can argue that quickly. So if I've got h1, h2, h3 and h4, and let's say that these are at positions 1, 5, 7 and 11, and our distance here, d, is going to be 13, then let's calculate how long it's going to take all of these horses to get back, right? Get back to the stable. And how I'm going to do that is I'm just going to assume that they're all moving at their maximum speeds, and let's say that their speeds are, so we'll say this is position, the speeds up here are going to be, let's say this moves at 7 ticks a second, this can move at 4 ticks a second, this can move at 6, and then this can move at 3. Okay? So you can see that the horses that we're closest to are moving a bit faster than the ones that are closer to the end point, but let's calculate it all the same. So assuming that the horses aren't following the politeness rule, how much time is it going to take each horse to get there? So for h1, it's going to take the horse 13 minus 1, that's the distance, divided by 7, that's the speed, right? So we'll get 12 on 7 seconds. Let's stick to seconds, assuming that they don't collide with anyone. Right, h2 will take 13 minus 5 on 4 is 2 seconds. h3 will take 13 minus 7 on 6, or 1 second to get there. And h4 will take 13 minus 11 on 3 is 2/3 of a second. I think I've done all my maths there correctly. And essentially what I'm going to say is that we can work upwards through this list, and wherever I see something is smaller than the one before it, in order to calculate the actual time it takes to get there, all I need to do is just turn that into the maximum of all the previous ones, right? So this is actually going to take 2 seconds. And let's maybe look at this quickly. So the way that I've set up the speeds, h4 and h3 get to the distance point without actually colliding. So h4 will get there in 2/3 of a second, and it will take an additional second for h3 to get there. And the same is true for h2, right? h2 is quite slow, and so h2 never catches up to h3 because h2 is moving slower than h3. Now h1, on the other hand, if it didn't have to follow the politeness rule, it would get there in, I think it was 12 on 7 seconds, which is slightly faster than 2 seconds. But because it will take h2 more than that time to get to the end, we know that at some point in time, h1 is going to crash with h2. Let's say it happens here, right? h1 is going to be moving at 7 kilometers a second over this section, and then it's going to be traveling at h2 speed for this section, right? So 4. But the important thing to note is that it's going to get to the stable at the same time that h2 does. So all I know, I don't even need to calculate like how long it's going to take this travel and how long it's going to take this travel. All I need to know is that it's going to take 2 seconds in total. Excuse me, sorry. Okay, so that's the idea. It is a bit of a greedy algorithm, so we don't need to do much computation. So I guess we can just get started with coding. And again, if you had trouble getting that concept, but now you got the idea, then now's your chance to pause the video and do some coding. Okay, let's transition to the VS Code scene. And let me just get the input and the output format first. So there's going to be a test case. Apologies for the keyboard, I will try and keep it low. So we're going to get the test numbers, and then for case in range, t+1. Right, so that's just going to be our loop structure to loop through each of the cases. Now each case is going to begin with two integers d and n, the destination and the number of horses. So those two. So this line here is just a bit of compact Python, so we're going to grab input, which is a single line, split it by spaces, and then turn everything in that list of characters separated by spaces into integers, right? So the input might be 3, 4. The split turns that into a list which contains 3 and 4, and then the map turns that into 3, 4. Right, so we're turning this string of integers with spaces into a list of integers. Right, so we've got d and n, and then n lines follow with the positions and the speeds of the horses, right? So horse info might be, we can do the same thing with this map inputs.split, and we can capture that n times, right? So now horse info I0 is going to be the position, and horse info I1 is going to be the speed. Okay, so now I need to calculate the slowest horse to get there. Is there any case where it's impossible to get there? Just trying to read through it quickly. Okay, no, we are saying the speed of each horse is positive, so that's okay. Cool. So for, let's just do say the maximum time required is going to be, let's say it's going to be infinite. So I know that the speed of each horse is at least 1, and the maximum distance, so maybe I'll go back to the Firefox thing quickly. So if we look at the limits here, we know that the speed of each horse is at least 1, and the maximum distance between any horse and the final position is going to be 10 to the 9. Right, so the maximum time it's going to take any horse to get there is going to be 10 to the 9 seconds. Right, so let's say, 10, let's just power 10, 9, and let's just add an extra 1,000 for posterity. That's the maximum time, and then I'm going to say for I in range n, right, so now I want to calculate how long it would take horse I to get there. So maximum time is going to be equal to, actually it should start off as 0, sorry, because we are going from minimum to maximum. Let's go -1. Right, so maximum time is going to be the max of the original maximal time and whatever time it takes this horse to get there. So that would be d minus horse info I0, right? So that's the distance that horse needs to travel. And I'm going to divide that by the speed of the horse, so horse info I1. And that's all we need to do in terms of Python. We just need to calculate the maximum time it's going to take any particular horse to get there. Now I know the maximum time. Now I know. So to calculate the maximum speed I can go at, all I need to do is take the distance I need to travel and divide it by the maximum time, right? So let us do that. So that is just d divided by max time, I believe. And then all we need to do is just print, what do we need? Case x, y, where x is the test case number, and y is the maximum constant speed, as long as it's within 10 to the -6 of the correct answer. Okay, so let's just print case number, case, max speed, and notice that in the range at the top here, I'm starting the indexing at 1 in order to ensure that this number case is correct for the output. Okay, I think that's all we needed to do, so let me just copy these sample tests into a file, so that one.in, right, and I'll get the output that we're expecting as well. So that's one.out with that. Okay, so for the first answer we want 101, then 100, 133. So let's try that. CD A And looks like we're in the clear. Okay, so they are all within 10 to the 6 of the, or 10 to the negative 6 of the answer we want. So let's try submitting that and see how we go. Takes a minute. Awesome. All right, we got that passed. So just to recap, we're getting the horse info and position. This is mainly just input that we're doing here. Then the only math that we need to do, because of that explaining that we did on the notes sheet, is we just need to calculate the maximum time a horse could take to get to the end, right? And that tells us how fast we can move, right? And just to go back to the notes, that was because, let me just get the notes up, sorry. That was because we made this initial little spot that the horse's speed, as long as it got there at the same time as the slowest horse, would be fine. And we also made the realization that collision in this case doesn't really matter, right? As soon as we collide, as soon as H3 collides with H4, they get to the stable at the same time, or the position at the same time. I don't remember what the wording was. Okay, let's have a look at the next problem. It's another horse-themed one, neighbors. Okay, I'll read the problem and then we'll give it a shot. So, you are lucky enough to own N pet unicorns. Each of your unicorns has either one or two of the following kinds of hairs in its mane: red hairs, yellow hairs, and blue hairs. Okay, but it can't have all three. The colour of mane depends on exactly which sorts of coloured hair it contains. A mane with only one colour of hair appears to be that colour. So blue is blue, red is red, yellow is yellow. And then red and yellow combines to make orange, yellow and blue combines to make green, and red and blue combines to make violet. Okay. So from there we get all the colours of the rainbow, Roy G. Biv. Yep. Oh, although excluding indigo, sorry. Yep. And the letters R, O, Y, G, and B, and V tell me how many of each type of unicorn I have. Okay. We've just built a circular stable with N stalls arranged in a ring such that each stall borders two other stalls. Okay, yes. You would like to put exactly one of your unicorns in each of these stalls. However, unicorns need to feel rare and special, so no unicorn can be next to another unicorn that shares at least one of the hair colours in its mane. Understood. For example, a unicorn with an orange mane cannot be next to a unicorn with a violet mane, since both of those manes have red hairs. Similarly, a unicorn with a green mane cannot be next to a unicorn with a yellow mane, blah blah blah. Is it possible to replace all the unicorns? If so, provide any one arrangement. I see. Cool. Okay. So let's go to notes and draw some stuff up. Let me add a new page, and I believe that was called, what, neighbors? Yeah. Okay. So, we've got these unicorns, right? What can I draw? There we go. Got unicorns, and the unicorns either have red hair, blue hair, or yellow hair. I'm going to say green hair because I don't have a yellow pen. Actually, I can change it, can't I? Yeah, okay, we've got yellow. Cool, and they also combine to give yellow and red gives orange, red and blue gives green, and yellow and blue gives green, and red and blue gives purple. Okay. And essentially we've got a certain amount of each of these colors of unicorns, and we want to arrange them in a ring of stores where each store has two neighbors, right? And essentially, if I have, say, a purple unicorn here, I can't have a unicorn that contains red or blue coloring in its mane in either of the sibling sections. So this one could be only yellow on each side in this example, right? Because we can't contain red or blue. So we also then can't contain orange because that's part red. We can't contain purple because that's red and blue, and we can't contain yellow, green because that's part blue, right? So as soon as we've got a purple here, we need to surround it with yellows. And I think that might actually be the first part that we can kind of tackle this problem from, right? As soon as we see a composite color, So as soon as we see a red, an orange, or a green, they need to be surrounded by the one composite, the one basic color that they're not part of. So as soon as I see an orange, I know I need to have a blue, because that's the only one that's not part of it. As soon as I need to surround it with blue, sorry. As soon as I see a purple, we already discussed that it needs to be surrounded by yellows. And as soon as I see a green, I know it needs to be surrounded by reds. Right? So I think that already motivates a lot of the algorithm here. So let me just think about this for a second. And I guess the only other restriction we have then is that as soon as I have a primary color, that can have the other primary colors next to it, or it can have its opposite next to it, right? So if I have a yellow, I can either have red, blue, or purple around it. And in particular, that means that if I place, let's say I've placed all of my composite colors first in some order. So if I've got purple here, for example, yellow here, for example, not yellow, it's not composite, sorry. Green here, and let's say we've got two oranges here. Then I already know what are next to each of them, and only some of them can be shared. So for example, this one in the middle could be blue shared, or there could be two blues in between, and then around the purple we can have yellows, and around the greens we can have reds. So notice that like everything that we've done now is kind of forced in that how we've had to place these. And after we've done this, all of the composite colors have been placed. So all that's left to do is place some more basic colors. And hopefully you can spot that we can really put these basic colors wherever in between these little breaks, right? And we're going to be completely fine. So I think that's all the algorithm we need to do. I'm going to place all of my composite colors. That's going to then require some basic colors, which if we don't have them, we're screwed and we say it's impossible. Then I'm going to place all of my remaining basic colors around the circle, right, in some other position. Because notice that yellow can always go with blue, blue can always go with red, red can always go with yellow, and so on and so forth. So this thing in the middle here could be a sequence of red, blues, and yellows in any order you want, as long as, okay, I've actually just forgot this, as long as the blues don't touch each other, so they need a yellow in between, right, or a red in between in each case. So we do need to be careful about that, I guess. I'm just trying to think. So maybe there's a bit more to this problem than I thought. Because now we have to be a bit careful, because I can also then split up these oranges into two blues if I want, and then add a yellow in here, if I need to get rid of, say, a yellow-blue pair. At the same time though, is there any benefit to doing that instead of just inserting it into one of these spots, right? So let me draw out another circle, because that one's getting a bit cluttered. Let's say I've only got one composite color, two composite colors. I've got two oranges, right? And therefore they need to be surrounded by blues. So let's put a blue here, and a blue here. I don't necessarily need to have a second blue here, right? Because they can be shared among the oranges. As long as there is nothing else in here, that's fine. And then I've got some extra colors. So let's say I've got two reds, let's say it's 4 blues, and a yellow. Let's actually say, and these are the extra colors I've got. Let's say I've got 3 yellows actually. So one way I could do this is I could have yellow, blue, yellow, blue, yellow, red, blue, red. I think that would work, because then I can just chuck blues in the middle and we're good, right? So that works. I guess the argument we want to make, and what I think is true, is that there is no point in us chucking some extra colors in between the two oranges there, right? So let's say I got rid of one of the blues, but I also chucked in a green there. right? Essentially, I got to remove one color from here on the largest color and one color from another one of my choosing. Now, if I wanted to say, then, you know, make this a bit easier on myself, now I can just draw without those two. I shouldn't have drawn green there, sorry, that should be a yellow. Right, so I've taken out a blue and I've taken out a yellow. But now the pattern on the outside is more or less the same, right? It's yellow, blue, red, blue, red, blue. Sorry, red, blue, red. I think that's it. There should have already been a blue there, sorry. So then we fill in blues here. And essentially it's the same thing, except we've removed these two from like somewhere in here. So I believe what the case is that as soon as we, as long as it's possible with all of the oranges clumped together, it will also be possible with all of the oranges separated. Oh, sorry, if it is possible with the oranges separated, it should also be possible with the oranges put together. Because if they're separated and there's these sequences, we can just find a way to chuck these sequences into the larger one. Right? The thing we need to be careful about, I guess, is actually, I think that's okay. Sorry, I just need a quick think. I'm suspecting that there might be issues when we've got multiple secondary colors and they're kind of interacting in weird ways, but honestly, if I'm in a contest condition, then I'm just going to assume what I've thought is correct and go with it. But let's see if I can think about it a bit more. So let's say, let me just scroll down a bit. Insert space, there we go. Let's say that we've got another circle here. We've got a pink unicorn here, and that's going to be surrounded by yellow unicorns. And let's say I've got two pink unicorns. Right, with a yellow unicorn here. That's not yellow. And then let's also have a green unicorn on the other side, which is surrounded by reds. Okay, so essentially what I want to do is I want to try force splitting this up, which I think is impossible. Right, let's say I've got some sequence. Actually, let's say I've got, okay, so let's say I have split it up and I've got a solution. So let's say that rather than drawing it like this, let's draw these two unicorns, these two pink unicorns apart a bit with their yellows. Let's say that I've got this sequence in the middle, S, right? I've got this sequence on the left, U, and this sequence on the right, V. And that works. The way I've assigned it works. What I essentially want to argue is that I can break up S and chuck them into U and V so that it works. And in fact, I think I can argue that I can merge U and V as well. So what do I know about the endpoints of U and S, right? It's kind of all I need to know. So for U, it either starts with a blue or a yellow. Again, we're assuming that I'm only left with primary colors. And on the right, it only ends with a blue or a red. One of those two. For S, I know both of them are compatible with yellow, right? So there must be red or blue on either side. Red or blue on either side. Yeah, what have I done? Why is this not drawing anymore? Okay, apologies about that. Okay, red or blue on either side. And then for V, it also needs to be capable. It looks the same as U, right? One of them is valid with yellow, which would be the blue and the red, and the other one is valid with red, so blue and yellow. So I think what we can do is, yes, okay. So essentially what I'm going to do is I can also take this yellow out at the same time, right? Because then it will be yellow, purple, yellow, purple, yellow. So what I might do is attach a yellow in between U and S, right? So I'm going to have U, yellow, S, and this will be my new U, right? I'll call that U dash. So notice that the end of U is already compatible with yellow, and the start of S is already compatible with yellow. So this is not going to cause any issues with the unicorn's constraints. So we can generate a new circle, which is going to have yellow, purple, yellow, purple, yellow. And then it's going to have red and green at the bottom. And then across the side, we're going to have U here. Then we're going to have a yellow, and then we're going to have S. It is our new one. And on the right, we're just going to have V. Okay, so that would work. So essentially, if we've got two of the same secondary color that are being split up and not combined, then we can always find a way to chuck in S into a different section U. Right? So our final solution is always going to look like, or can always look like, a number of purples together with yellows. Right? So yellow, 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 yellow. A number of greens together with reds. And then a number of oranges together with blues. Right? So I'll just say I've got one there. And essentially the only choice we have in the matter now is what goes in this section of anything, what goes in this section of anything, and what goes in this section of anything. And I think for that one, we do still have to think a bit about it. So essentially, I think what we need to do is we can do it greedily. So I'll have a list of how much I've got left, right? So I've got, say, let's say I've got 5 blues, 3 yellows, and 2 reds. And what I'm going to do is I'm always going to try place the largest color I can, right? So my blue could go, well, it couldn't go in here for now, but it could go, for example, in here. So I'll chuck a blue in there to begin with. And I'm going to try chuck the blue so that it covers the second most abundant color, right? So yeah, this blue is going to cover this yellow, essentially. So now you'll notice that I can't place any more blues. So for my next step, rather than trying to place another blue, I'm going to try to place a yellow. Right, and a yellow can go in either of these 2 sections. So I'm just going to chuck it in front of one of the sections that has a blue, because that's the most abundant color. So I'll chuck a yellow here. And now that reduces to 2 yellows. And now notice that I can chuck a blue down, so I'm going to chuck a blue down to cover the yellow. And that goes down to 3 blues. Now I can't chuck a blue down, but I can chuck a yellow down, so I'll chuck the yellow down here to cover this blue. So now there is 1 yellow left. And now again I can place a blue, so now I place the blue here to give me 2 blues left. And I've still got 1 yellow left, so let's place a yellow here, in between these 2. Sorry if it's a bit hard to see, but that's just here. So now we've got 0 yellows left, 2 blues and 2 reds. Now I can't place a blue at the moment in these sections. No, I can't place a blue at the moment because the sections that are left over is the space in between these 2, the space in between these 2, and the space in between these 2. But I can place a red, right? So I'll place a red over the one that's got the least remaining, which is blue. And now I can place my blue, and then my red, and then my blue. Right, so essentially I'm always greedily placing the largest amount of color I have left. And for that largest amount of color, I'm always going to be placing it over the next most abundant color that I can, if possible, right? Okay, so I guess we've got 3 cases to consider. There's the case where we've got only a single secondary color, in which we've only got 1 section, and the answer is very easy. There is the case where we've got 2 sections of secondary colors, and so we've got 2 sections of unused areas. And then we've got 3 sections of secondary colors, and so we've got 3 sections of unused areas. Alright, let's give this a shot at coding, because I think we've been looking at diagrams for a fair while. Let's go back to just reading the problem statement quickly. So for the input, we're just getting the numbers of each color, and then for the output, it's just a possible ordering. Okay, cool. Let us go back to the code view and give that a shot. So I'm assuming this one's going to be a bit more implementation heavy, just by the way we've described it, but let's give it a go. So we're going to get the number of test cases. I'm going to do the exact same code as I did before, where we've got this case, and then at the end I want to print case number case, and the answer to that is going to be some value which we don't quite know yet. Okay. Then we're going to be reading N, R, O, Y, G, B, and V. O, Y, G, B, and V. I'll use the same trick as before. Something going on with my throat. Okay. So N is the number of unicorns, and then the sum of R, O, Y, G, B, and V should be the total number. So first of all, we need to place all secondary colors. Now, if so I guess we've got a few cases to consider now. So if G equals 0 and O equals 0 and V equals 0. I think I meant saying purple, but I meant violet. Then no secondaries. So just follow greedily. So let's say, how do I want to do this? Okay, let's go through this quickly. So what I'm going to do is I'm going to store a list which contains the red count, the green count, the blue count that I can just keep sorting. So I'm just going to say counts is equal to R for red, B for blue, and Y for yellow. And I'll do counts.sort, and I guess I want to reverse it. So we'll just do counts equals counts anyone. Right, so now actually we don't need to reverse it. Okay, so I'm going to sort it, and I'm essentially using the fact that when tuples sort, they sort by their first index first, right? So I'm sorting by R, B, and Y at the moment. So what I want to do now is keep trying to place these primary colors. So let's say that the current endpoints is equal to nothing. And essentially what that means is that current endpoints is going to contain up to 3 different lists, and each of those lists is telling you the left endpoint and the right endpoint of the open section. So we've got a particularly annoying case for the case where we've got no secondary colors because we haven't placed any colors yet. So what I'm going to do for that is I'm just going to place one of the colors and reduce that count by 1. So I'm going to place the red one here. So I'm going to say, not red, let's say I'm going to place the first one, or the one with the least colors in it at the moment. So the current endpoint is going to be counts 0, 1 to counts 0, 1. Counts 0, 0 is going to decrement by 1. So that's picking color count 0. And yeah. I guess we also need to generate a list at the end of this. That's painful. So let's start off by saying, that's very painful actually. I feel like I might be going over this in a bit weird way, which means the code writing is not going to be the cleanest. But I also can't really think of a way to simplify it, so we're just going to have to go for a bit complicated, I guess. So we're going to have a list of our current endpoints, but we also need a list of where they are in our actual list as well. So let's say current solution is going to be equal to nothing at the moment except for counts 0, 1. And on each of the endpoints, I'm going to be storing the index of the left-hand side of the section and the index of the right-hand side of the section. So that's going to be, in this case, 0 and 0 are these positions. And what I'm now going to do is say while the sum of v1 for v in counts is greater than 0, so while there are still colors, and we'll have a flag to tell us whether we've found something that's impossible. So now I'm going to say for y in range 3, let's say for y in range 2, -1, -1. Essentially what I want to do is I want to move backwards through the count list and try to place one of those colors, right? So for y in range 2, -1, -1. Try to place counts of y. Yes. Yep. Okay. So try to place counts of y. So now I'm going to go for end in current endpoints. If if end 0 is not equal to counts y1 and end 1 is not equal to counts y1. So what is that saying? That's saying, well, let's actually draw some stuff because this is very confusing at the moment. Let me just go back to the note scene. So we've got, let me insert a space. We've got current endpoints, which I'm just going to call current end here, and we also have counts. So let's say that I've got some reds, some blues, and some yellows left. Let's say that I've got 6, 4, and 3. And let's say that my current solution, and I'm just going to represent this as a list that loops around at the end. Let's say our current solution is, say, blue, red, yellow. And that essentially we can insert colors into this section, and we can also insert colors into this section, right? The way I would write that is that the current end, in this case, is going to be, well, red, blue, and their indexes are, sorry, red, yellow, and their indexes are 1 and 2, and the other endpoint is yellow, blue, and their indexes are 2, 0. Right, so these are the current inserting positions that we could go into. One of them is between red and yellow at positions 1 and 2, and one of them is between yellow and blue, which is between indexes 2 and 0. Okay, so that's what current end is, and what counts is just a sorted list containing all of the colors. So in this case, you'd represent that as 3y, 4 blue, and 6 red. Okay, so that's what counts is, and that's what current end is at the top. So with that, let's try to go back to the code and push a bit forward. So what I'm saying when end 0 is not a good accounts y1 and end 1 is not a good accounts y1, that's saying that whatever color we're looking at in counts y, it's not at either of the endpoints of this insert position. So this is possible. This insert position is possible. And let's also say I was, so possible is that For I in enumerates, so I just want to capture that this is possible essentially. So I just want to do possible dot append I. Right. If there's nothing possible, then we should continue. Otherwise, something possible, insert. I want to choose to insert on the least, on the most abundant color, if it is available, right? So essentially, if there is one endpoint that is not equal to counts, hang on. Yeah, so I'm just going to say for z in range to -1, -1. I'm going to, and then for, yeah, so for pos in possible, is there a z color, or counts z color endpoint on pos, on insert position pos? Right, so if current endpoints pos 0 is z, no, I should say counts z1, or same stuff but for the right hand side of that insertion point. In fact, I'm actually going to separate this into two different if statements. If that was the case. Okay, so if we want to insert on the left endpoint here, then I'm going to set current endpoints pos 0 equal to counts y1. I'm going to set counts y0 minus equals 1. And I need to then also insert into our current solution, insert at the position where our current endpoint is, right? So I want to insert at current endpoints pos 2. Insert, actually I want to insert just after. So I want to insert that at just after that point. And the object I'm going to insert is counts y1, and that also means that current endpoints pos 2 is going to be equal to current endpoints pos 2 plus 1, right? Because we've changed the index of our end position, and we also need to update the indices of all other end positions that have moved. So what does that entail? Let me just double check. Yes, okay, so by inserting into that list at that point in time, anything that comes after that list we need to increment by 1. So let me actually just do that here instead. So for, let's say, for I2 in range when current endpoints, for J2 in range 3, oh no, sorry, I should say in range, no, yeah, we can do for J2 in range 2. If current endpoints I2 of J2, where J can go from 2 to 4, is less than or equal to where we're inserting into, I need to increment this by 1. Yep, so if I'm inserting on the left-hand side of a region, everything that is past that point needs to get its index updated. And then I can update my own index. But actually this should just be larger, sorry. Yeah, so if it's larger, then that's where I'm inserting. Cool. And also if it's the same position, which is only true if current endpoints pos 3 equals current endpoints pos 2, type. Then I should also say, and that should happen before I increment. Then I set pos3 equal to the same thing. Okay, so that is the case where we're inserting onto the left-hand side of a region, right? And let's also go through what that is on the notes. Let me just have a look at that. So let's say that with this current endpoint that I've got on the left here, I'm going to try inserting, sorry, not counts there. I'm going to try inserting into this current end. Let's say I'm going to insert a blue at this position in between the red and the yellow, right? So the way that current end needs to update is that we're going to have R, B, sorry, B, Y, I should say, because we're inserting on the left-hand side of the section. B, Y, with indices 2 and 3. So notice that the 2 on the other side has also increased. And then our other section is going to be Y, B still, but the indexes are now 3, 0. Right, so everything that was already there got updated. So we went from 1, 2 to 2, 3, and we went from 2, 0 to 3, 0. Right, and the only other thing that we replaced is that now B is the left-hand side of this section, so rather than having RY, it's now BY. So that's all we're doing there. Right, let's go back to the code and see if we can do the other half of that. If current endpoints pos1 is Z1, counts Z1, then we can insert on the right-hand side instead. So current endpoints pos1 is going to be counts y1. So this is going to look very similar to the code above. I'm going to reduce counts y0. I'm going to insert into my current solution. Now the difference here is that because I'm inserting on the left-hand side of a number rather than the right-hand side, I don't have the +1 here. Right? So I've removed the +1. Now I need to do the same thing with updating indices. So I in range len current endpoints for J2 in range 2, 4 if current endpoints I2 J2 is greater than or equal to the current endpoints at pos2. Actually, let's save pos is current endpoints pos2. Can't type. Right, so if it's greater than or equal to the saved position that we're inserting at, then we need to increment. So current endpoints I2 J2 plus equals 1. And then I just need to say that current endpoints pos2 is equal to saved pos. And we also have to have the same check here. So if, and I should be saying 3, sorry, not 2 here. It should all be 3s and not 2s. And these should be, okay, that is correct, and that is correct. Yep. Then we're going to insert a position 3 on our current solution, yes. Then we're going to update 3 to the saved position. Then if current endpoints 3 is equal to current endpoints 2 minus 1, then we're going to set them to be equal, where current position 2 is equal to current position 3. So essentially, like if they already started off as the same value, they were already pointing at the same index and it's kind of reflexive, then in this process we would have incremented current endpoints pos2 by the same value as current endpoints pos3. What we can actually do to make this maybe a bit more clearer is this. So if they were already the same value, then they would have stayed the same value after this transformation with the for loops, at which point I can set current endpoints pos2 also to the saved pos. I think that's clearer. Okay. And I think that's everything to place. So for pos impossible, for z in range, and I need to also have some marker that says, you know, place is false if I place something, then placed is true, and then I will break. And I'll do that in both these cases. And now, if placed, then I will also break, right? So I know I'm only going to place one of these at the end of that for loop. And then all I need to do in my while loop, I guess, is then update the counts. Yes, I need to update the counts. So counts dot sort. Well, I don't need to update them, sorry, because they've been updated on the insertion, but I need to resort them so that I'm dealing with the largest one again. Okay, so I've sorted my counts, and then I can break, right? Because I've gone through and found a possible position. Now, one cool trick that you can do in Python is I can use this else block here to check whether this for loop broke at all. If it didn't break and there was never anything possible, then we will get to this else code. Now, if it's the else code, then I can say bad equals true and break. Otherwise, we'll get out of this while loop. So now we know that if we get out of this while loop, bad tells us if we couldn't insert at any point in time, then that's going to be bad, and we can't, and we'll say it's impossible. If bad is false, then current solution, should just have the solution that we can print out, okay? So I think what we can actually do is remove this from the particular case where we've got no secondary colors, because I think that this kind of part of the code is all the same. The only thing that will be different, say, if G equals 0 and O equals 0, I'm just dealing with the different cases where, well, actually, no, I can do this a lot better. No, let's leave it like this. And G equals 0, and V equals 0, or, so I'm just dealing with the cases where we've only got one secondary color in this case. G0 or O0 and V0, one secondary. Right, so the counts, so the current solution, I guess we can have different cases now. So if G equal to 0, sorry, if G not equal to 0, then, so I guess this should be an else if. If G is not equal to 0, then G is the one secondary, so our current solution, well, I need to first assert, no, not assert, but say if G needs to be surrounded by reds, so if R is greater than G, then it's possible. So if R is less than or equal to G, then we're going to say bad equals true. So while not bad, and I might actually add to that while loop, so that just ensures that we're going to not do the while loop while we've got some bad results. And I should say bad false starts up here. Where did I originally define bad? Here. So let's just keep that there. Yep. Otherwise, then our current solution is going to be our current solution. We kind of want to zip together these values, but what I might just do is it's just painful. I don't like doing this stuff because I've got an interleaf, which is always annoying. Okay, so let's say R if I mod2 is 0, else G for I in range 2 times G plus 1, right? 0 up to 2G. Yes, okay, that sounds right. So essentially, what this is going to end up being is RG, 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 R, ending on an R and covering all of the Gs. So I've got my current solution. My current endpoints is going to be just one endpoint, which is counts. So it's going to be R, R, and the endpoints are going to be 2 times G and 0. And my current solution, sorry, my current solution is already defined, so my counts now is just going to be r minus 2 times g plus 1, oh, sorry, minus 2 times g minus 1, I should say, and then b and y are the same. Right, so that's just simulating the fact that I've removed 2 times g plus 1 r's, creating the original solution here. Okay, and then we have the same thing for, let's say O is next. Right, so O is red and yellow, and so requires a blue. So B O for I in range 2 times O plus 1. The current endpoints are B and B with 2 times O. And then my counts are B with B minus 2 times O minus 1, R with R, and Y with Y. Okay, and then finally we have the final secondary value, which is if V is not equal to 0, which requires yellow. Our current solution is then yellow or violet. I in range 2 times V. The endpoints are yellow and yellow with the same indexing, 2 times V. And then the counts are Y minus 2 times V yellows and R reds. Right, and then all we need to do is just counts.sort, I guess. But I should probably do that in each of these just to be safe. So let me just paste those again. Okay, and I believe that's the one secondary color case handled. Now we can deal with the cases where we've got 2 secondaries, so LF G equals 0. I know that 2 secondary O and V. And now my current solution is very similar, so it's just this, sorry, it's just this one plus, can't type, this one plus this one, right? My current endpoints is then just going to be equal to, well, we've got one endpoint which is B to Y, and I shouldn't be making all of these lists rather than tuples actually. Let me just make sure I'm doing that, because we are going to need to change these values. Same with the counts array. It's a bit painful, isn't it? I should have just done this to begin with. So I believe with the CodeJam rounds you get 2.5 hours in the round 1. So we are still well within time, even though we are doing all this explanation. So it's completely feasible for you guys to give this a shot when CodeJam does become available. I forget when that is. It's sometime earlier in the year. I think that's all lists now. Okay, so my current endpoints is now going to be B to Y, and the indexing on that is going to be 2 times O to 2 times O plus 1, and the other endpoint is Y to B with 2 times O plus 2 times V and 0, I believe. Let me just double check. So if we've got, for example, B O B O B and then Y V Y, then the index on this is going to be 0, 1, 2, 3, 4, 5, 6, 7, which is not quite equal, is it? No, I believe this should be a plus 1. Apologies. Yes, yeah, it should be a plus 1. That makes sense. Okay, so that's our current solution, our current endpoints. Counts is going to be equal to essentially this one combined with this one. So you can see there's a lot of code repetition here. The other thing we need to do is check, if y is less than or equal to v, that is true. L if b is less than or equal to 0, that is true. And only else are we doing this stuff here. Right, then we've got the same thing for when O is equal to 0, so this is going to look very similar to what we've got up here. Except we'll be copy pasting different parts of the code above. Okay, so rather than having B, O, we'll have RG. Our current solution isn't going to include the B's, but will instead include the R's and the G's. Our current endpoints is still going to start looking like, our current endpoints is now going to be RY and YR with very similar values, except we've got G's here instead of O's. And our counts is going to look similar to before, except rather than changing B and Y, we're going to be changing R and Y. Okay. And then we also finally have L if V is equal to 0. So again, this is going to look very similar to this one, except we're going to be replacing all of the code with V with all of the code for R. Sorry, for G, I should say. So we'll replace that one. Our current solution will then replace this section of Y. There. Our current endpoints are now going to be BR, RB with 2 times O, 2 times V would be replaced with 2 times G. And then the counts is going to just have YY, but now R minus 2 times G minus 1. Okay, now the only final one to deal with is 3 secondary colors. And this again is just going to look like a combination of the 2 secondary colors with the third one now. So now our current solution now combines 3 different values rather than 2. So let's say we've got B, R, and then Y here. Where is that? Here. So let me just actually put this on a few different lines so that we can see all of that. So we've got the section of BO, 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 then RG, 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 then YB, YB, YB. Right, then our current endpoints is going to be equal to, well, we've got 3 endpoints now. So the first one is going to be BR at 2 times O, 2 times O plus 1. The next one is going to be RY at 2 times O plus 1 plus 2 times G, and that goes to 2 times O plus 1 plus 2 times G plus 1. Bit of a mouthful there. Then we've got Y to B, which is going at now plus 2 times V plus 1 to 0. That should only have 2 plus 1s actually. Yep. I believe that is working. We can test that in a bit. We just need to update the counts now, so the counts is going to look very similar to before, except we're going to have the same minus 2 times V minus 1 for all 3 of them. And I think that is good. I think that's everything. There's a lot going on there, but I think that's all the cases we needed to cover. I'm getting kind of scared now because it's going to very easily break because I haven't been testing anything, but let's hope all goes well. So let me just go to sample input. We can have a look. Okay. So 1.in has 4 different test cases for us to check against. Let's just try it out and see what it spits out. It's probably going to break. But that's okay, we can figure out what's going on. Okay, well that's an easy problem to fix. We forgot to print anything here. So if bad, we want to print impossible. Oop. Otherwise, we already have a solution. So we can, oh, and this should not be in braces. So. Otherwise, we want to print join current solution. I believe that's everything. Okay. Okay, we've got issues with tuples. That's okay. We just need to make sure that we're defining tuples for everything, which we did not do in the first case. So let's go back and fix that. Yep. Again, more tuples, defining correctly. Why am I missing? Oh, should be there. Oh, I see, sorry. These should be V0s in our while loop. So we've got a while loop here. Remember, what we're doing is trying to say while there are still colors, but in the counts, the first value, or V0, is the number of numbers left, not strings, not V1. Okay, this hasn't finished immediately, so it's crashed somewhere. So let's say, let's print placed. Let's print placed and see if it is infinitely placing things or if it's only placing a finite number of things. It's never even getting to that point. Okay, that's a bit concerning. So we're never even getting to this point, so we're never even having pos and possible, I guess. Oh, okay. That's a bug. Okay, so if there's nothing possible, then we want to continue. Not if this is not 0. Whoops. Okay. Seems like we've got some answers. So let's see if they match up. Or if they make sense in the first place. No, so apparently case 2 is possible in our case, but it shouldn't be. Right? Case 2 is saying that there is 3 colors. Yeah, there's 3 colors in total. There is 1 red and 2 yellows, I think is what that says. 1 red and 2 yellows. Yes, 1 red and 2 yellows. So why are we placing a blue? It doesn't seem right. Oh, okay, I need to be a bit careful here. So when we're placing colors, we need to make sure that the place I'm trying to, the color I'm trying to place still has some values, right? So if counts, if counts y1 is equal to 0, so if there's no available amounts of this color to place anymore, then I should just continue because I can't actually place it. Still trying to place BYR. This should be Y0, sorry. Okay, no, it's still got the same issue. Why is it placing a B there? Oh, that's why. Okay. So in this case, where I'm placing that, I should actually be placing the most, yeah, I should be placing the most, what's the word for it? The most abundant color, right? So in this case, in this test case that we're looking at, case 2, we've got 0, B, 1, I think it's 1R, and then 2y. And what I was previously doing was placing the b here, which was count 0, but I should be placing the y here and count -1. So now if I run it, it's still working somehow. Oh, because it's reducing the count of the wrong thing. That should be that. Now it's saying it's impossible. Okay, so case 2 seems to work now. Case 1, does that work? And case 4 should not be impossible. So let's double check both of those. So we've got 6 colors here, 1 red. I'm just gonna put, what is it? N-R-O-Y-G-B-B. Okay. So we can tell what's going on. Okay, so in this first test case, we've got 2 reds, 2 yellows, and 2 blues, so no secondary colors. So YBR, BYR works. That is a possible solution. And I believe it lines up. Yeah, it lines up with the cases on the site. The third case here, we've got 2 reds, 1 yellow, 1 green, and 2 blues. So the green is surrounded by reds, which is good. And then BY fits in well here, which again lines up with the test case. Is it long enough though? Shouldn't there be 6 numbers here? There should be. So this isn't actually correct because I should be placing another B. That is interesting. Why is that not placing a 6th character there? So current solution, so start off with RGR, then we place BY, then what is next? The next time we update current solution is down here. No, it should be fine. Inserting into current solution. So what I might do is I'll print counts and current solution at the end of each step here, or at the start of each step here. So might play that. So for case 3, that got me RGBY. Oh, we have -1s here. That is an issue. Why are we getting -1s for the R's? So that is why I'm not placing the last character, because I'm reducing the amount of R's I have by too much. Oh, of course. Okay, so I'm not placing 2 times V minus 1 Y's to surround the purples or the violets with Y's. I'm only placing V minus 1 of them. So the counts array is currently incorrect. Apologies if somebody spotted that earlier. But this should just be O minus 1, G minus 1, V minus 1, G minus 1, O minus 1, V minus 1, V minus 1, O minus 1, G minus 1. I think we're good there. Okay, so now if I run it, now we get the 6 characters RGR, BYB. The last case works. Case 4 is instantly impossible, apparently. So let's remind ourselves what case 4 is. So with case 4, we have 2 Y's and 2 V's. Oh, I see. So there is one case that we haven't dealt with, and it's when we've only got two different colors. One of them is what am I saying? One of them is a secondary, and the other one is its complementary color, right? So in this case, we've only got V and we've only got Y. In that case, let me just go to the notes quickly. We do have another solution, which I hadn't considered, which is that we'll draw purple here, purple here, purple here, and then we'll have yellow here, yellow here, yellow here, right? So we're using one less yellow in the process. So that's the only other way that that's possible. Now, let's just add that into the code quickly. So essentially that can only happen in our code when we're in this elif statement, so when we've got one secondary color. If G is not equal to 0, and r is less than or equal to g, then what we can say instead is that if, so we'll do the bad equals true after, if r equals g and r plus g is equal to n, right, so essentially we're looking at the final case for case 4, then all we need to say is the current solution is equal to r if I mod to 0, else g for I in range 2 times g. I'll just say that my current endpoints are empty, right? There's no way to insert to, and my counts are empty. Doesn't really matter as long as I have the correct current solution. Otherwise, I'm going to say it's bad. Right, and I'll do the same thing with b and o. So if b equals o and b plus o equals n, then the current solution is going to be b o for I in range 2 times b, and we're fine. And the same thing for y and v. So if y equals v and y plus v is equal to n, then we've got y v alternating for I in range 2 times v, and we're good. So if I run that again, now we have a solution. Okay, so let's remove that print statement and just make sure that all of those are giving us reasonable answers. And I think all of that lines up with what we've got on the site. So I'm a bit skeptical that it's going to work. I think there's some case I probably missed, but let's give a submission a check and see what it does. I'm just gonna have a quick drink because I've been talking for a while. Wrong answer. Okay. I think I've been talking about this problem enough, really. I don't think you or me are going to be getting much out of debugging this code, to be completely honest. But if you did want to fix this, what I would say is just come up with more test cases. I would probably try turn these test cases that I've got on these nodes file into actual test cases. Let me just go back to the nodes file, sorry. I would try turning these into test cases so that you know what's going on. I don't know why I can't scroll. Looks like nodes has died. And then see if you can spot something that doesn't look like it should be going on. There's probably something a bit obvious that I'm missing here, and apologies if I've been making some assumption the entire time that you've been yelling at me for. But since we've maybe only got about an hour to discuss stuff, I'll have a read through the third question and see what we can discuss about it. So let me just get that back up. Oh well, you can't win them all. Alright, Pony Express. Let me just have a drink, sorry. Okay, it's the year 1860. Pony Express is the fastest mail delivery system joining the east and west coast of the United States. We've got another east-west problem. The system serves n different cities. In each city there is one horse, as in the expression one horse town. Each horse travels at a certain constant speed and has a maximum total distance it can travel before it becomes too tired to continue. Okay, so we've got n cities, each containing a horse. They each can have a constant speed that they travel at and a maximum total distance. The Pony Express rider starts off on the starting city's horse. Every time the rider reaches a city, they may continue to use their current horse or switch to that city's horse, where switching is instantaneous. Horses never get a chance to rest, so whenever part of a horse's maximum total distance is used up, it is used up forever. When the rider reaches the destination city, the mail is delivered. The routes between cities were established via complicated negotiation between company owners, lawmakers, union delegates, and Cousin Pete. That means that the distances between cities do not necessarily follow common sense. For instance, they do not necessarily comply with the triangle inequality, and the distance from city A to city B might be different from the distance from city B to city A. Okay, so we've got a directed graph of distances between cities, sure. You're a time-traveling entrepreneur and you bought a very fast computer from the future. A single computer is not enough for you to set up an email service and make the Pony Express obsolete, but you can use it to make optimal routing paths for the Pony Express. So given all data about the routes between cities and the horse in each city, and a list of pairs of starting and ending cities, can you quickly calculate the minimum time necessary for each delivery? Treat all of these deliveries as independent. Using cities and horses on one route does not make them unavailable on other routes. Okay, so import is going to start on each test case with with two integers, the number of cities with horses and the number of pairs of stops we are interested in. Cities are numbered 1 to n. N lines, each containing two integers, the maximum total distance the horse in the other city can go, and the constant speed in kilometers per hour at which the horse travels. N lines, each containing n integers. The jth on the ith of these lines, Tij is -1. There's no direct route from the ith to today's city. Q lines containing UK and VK, the starting and destination point respectively. Okay. Okay, let's write this up in notes. There's a lot going on with this problem. I'm not sure I'm going to be able to solve it, but we'll give it a shot. The name of the problem was Pony Express. Pony Express. So, we've got these cities that form a graph structure. Is at the heart of the problem, so we might have 4 cities here. We'll call that city 1, 2, 3, and 4. They each have their own horse, and all of these are also part of some graph structure with directed weighted edges. Right, so it might take us 4 kilometers to get here, 10 kilometers to go this way, 15 to go this way, 13 to go this way. Maybe I can go down here at speed 2 and up here at speed 3. Okay. And essentially I need to find the shortest path between 2 points, say from 1 to 3, assuming that I have to take a horse across each path, and horse each has a maximum distance they can travel. Okay. I think there's 2 things that are worth noting. The first is that any path, no matter what, always needs... Okay. Yes, okay, this is useful to state. So for any path that we make, we're never going to get on the same horse twice, right? Because if I jump off a horse at some point, then there's really no point in me coming back to pick it up at some point, because it means I've done a full cycle without really doing anything other than maybe moving the positions of horses. But again, if I care about the positions of horses, I can just get on that horse. I stay on that horse and I'm leaving and just keep taking it anyway. So, thing number 1 to state. We should never... what am I saying? We should never jump on a horse twice. I believe that makes sense. I just wrote believe. Horse twice. Right? As soon as we jump on a horse, we're going to take it as far as we want to and then get off somewhere else. Number 2, I guess, is that... what is that? Let me just double check what the input size is for this problem, because that might change my idea. So for each test case, and there are 100 test cases, we will have 100 queries per graph, and the graph size is at most 100 vertices as well. So relatively small, I would say. Let me just double check. So we've got 100 vertices, 100 queries, and 100 tests per query. So I guess we've got 10 to the 6 in total, actually. So I want each query to take more or less constant. Oh no, I want each sorry, each query to take more or less linear time to answer if I want to be within time limits. So we know we should never jump on a horse twice. I'm thinking we can do something like a pre-computed Dijkstra's where we add some more edges to specify where a horse can actually go to. The only issue there is that okay, actually I think that works. So, and this kind of piggybacks off the fact that we should never jump on the same horse twice. So let's say that I start off at vertex number 1 with horse number 1. Now, what I need to calculate on my graph is what vertices can horse 1 get to, right? Before I have to jump off, and what their distances are. So we can do that by pre-computing Dijkstra's on this graph, but it might mean that I go from node 1 to node 2, and then node 2 to node 3, and that takes me 6 kilometers, and by that point maybe I can't make the 9 kilometers to get to number 4. So the fastest that I can get to node 3, for example, is going to be the horse 1 speed, the distance, 6, divided by the horse 1 speed, right? And that will tell me like how fast I can get to node 3, at which point I need to jump off and pick a new horse, right? So essentially what I'm going to do there then is say, well, the fastest I can get to node 2 with only horse 1 is 4 on S1, and the fastest I can get to node 3 from node 1 only using horse 1 is 6 on S1, right? So essentially I've got a graph for horse 1 which just looks like this. We've just got 4 on S1 here and 6 on S1 here. Now I'm going to do the same thing from position 2. So assuming that we start off at position 2, well, where could I go? I could go straight to number 1, and let's say that the horse here can run at most 11 kilometers. Right, so the direction this way is going to be 10 on S1. Right, the direction this way is going to be 2 on S1, and then I can go this way to node 4. Let me draw in the nodes, sorry. So this is 2, 1, 3, and 4. I shouldn't be drawing that edge, sorry. I should be drawing this blue edge here, right, to signify that it'll take us 5 kilometers to go from 2 to 3 to 4, and the speed at which we'll achieve that is divided by S2, and these should all be S2 as well. Right, so essentially the edge that I'm generating here is if I have an edge from node 2 to node 4, then it's telling me that I can take the horse at city 2 and ride them all the way to city 4, and the time it will take me is this here. Let's do the same thing in green for node 3. So node 3 can only go to node 4, and let's say that then takes 3 on S3 to do, and then 4 can't go anywhere. So that's our entire graph. Now, what I claim is that the shortest path on this is the best path for us. Right, so let's say that we wanted to get from 1 to 4, right? If I wanted to start at 1 and end at 4, I've got a few options. First of all, I could try riding horse 1 all the way to node 4. Now, if this was possible, then in this graph here, there would be an edge from 1 to 4, and it would tell us how long that would take. The other option is that I take horse 1 to some other node and then pick up their horse, right? So I could ride my horse from node 1 to node 2, and it would take this long. At which point, I could get on the horse at city 2 and then ride at this amount. Or, I've got a few other options actually. I could ride the horse at city 2 to the horse at city 3 with this much time, and then the horse at city 3 to the horse at city 4 with this much time. Right, so essentially, when we're moving through the graph, rather than this being a strict path from 1 to 2, what this actually is I'm riding my horse from 1 to 3 to 2, for example, and then I might be riding horse number 2 from 2 to 3, and then horse number 2 from 3 to 4. So every time I'm moving along an edge in this graph, I'm actually moving along multiple edges in the original graph. But essentially the idea is very simple, right? We're generating this graph, which is, you know, A connects to B, means that horse A has a path from A to B. And then all we need to do is figure out, well, if that's the case, if horse A has a path from A to B, then if I can find the shortest path from 1 to 4 on this graph, that tells me the shortest path from 1 to 4 swapping horses on the original graph. I think that just works. This implementation might actually be a lot simpler than it was for the second problem, which actually kind of tends to be the case with what I understand, because the third question is normally going to be a harder question, and so there's a lot less implementation details. Let's just double check the rest of the problem definition, make sure I'm not missing anything. So for the output, all I need to do is the minimum time in hours to go from city UK to city VK. Yeah, okay, I think that works. So we are going to need to implement Dijkstra's along the way, which might be a bit painful for some people, but I think I've written it enough times to know what I'm doing. Okay, but we've went over the majority of how the problem works, so now's your chance to write the code yourself if you want, and I'll start doing my solution now. Let me just get up the code. Okay, so let's make solution.py. Same thing as before, we're going to get the test case number and do for case in range 1 to t plus 1, and then at the end of the day we'll be printing case number case is some answer. Okay, so now we need to read in, what is it? We need to read in N and Q, the number of cities and the number of pairs. NQ is just mappings input.split. Then what's next? N lines, which contain 2 integers e, the maximum total distance, and the speed of the horse. So the horse info, again, is going to be this for blank range n. Right, so again we've got horse info I 0 is the maximum distance, and horse info I1 is the speed. The next n lines is going to contain n integers, so this is our adjacency matrix. So we can write the same thing here. So adj ij is -1, means no path. Adj ij is not -1 but is equal to a, means distance a between cities I and j. Yep. And then Q lines, so queries, again with the same format except we have Q of them. So, you know, we're asking for the path from queries I0 to queries I1. Okay, so we've got a few steps in this. So step 1 is just to compute the auxiliary graph that we wrote in notes, right? We just want to compute we just want to be computing, what's happened to my thing? Why is this going all over the place? Okay, we just want to be computing this graph here on the right, yeah? So we just need to run Dijkstra's on our graph. Okay. So the first thing I want to do, I believe actually we might need 2 auxiliary graphs now that I think about it. Yes, okay. Yeah, let's go with that. Okay. So I'm going to create a copy of the adjacency list, and this is going to be shortest distance. And that's just going to be edge ij for j in range n for I in range n. Right, so that's just a deep copy of the adjacency list. And now I'm going to run Dijkstra's on every source node, right? So for source in range n, and let me just import the heap q module at the top. All right, we're going to run Dijkstra's from source. So I have my list of expanded nodes, which is going to be that, and then I will do heap q dot heap push 0 and source. Then we've got, I guess, expanded actually should be false times n. Yes. And I'll just call this q. Sorry, writing this a bit all over the place. So q is going to be this list, and I'm going to push the source node onto the q with a weight of 0 because that's the current distance. Then, okay. Yep. So then I'm just going to say while q, then the distance and the vertex is going to be heap q dot heap pop. Where is heap pop? Of q, right? If expanded v, sorry, if expanded v, then I continue. If we're not expanded, then I set expanded v is true, and then I want to go through all children. And update. I'm noticing that this could actually be too slow for the time bounds, but let's work on it anyway and see what happens. Go through all children and update, or add them to the queue. Right, so for I in range n, if edge I, no, it should be edge vi is, yes, if edge vi is not equal to -1, then d2 is d plus edge vi. So this is the distance from the source to I. So again, if I equals source, I guess we should be continuing. Or I guess in general, if expanded of I already, if we've already looked at I, then we should continue. But if adjacent vi is not -1, so there is a path between them, so the distance should be d2 there. We can do heap q dot heap push q, and then we're going to be pushing d2 with I. And then the only other thing we need to do is then just keep updating our adjacency list. So we're adding these extra edges. So yeah. So whenever I get D and V off of the heap and it's not expanded already, then I want to set adjacency, or not adjacency, but shortest distance, I should be, sorry. So shortest distance of source to V, yep, is equal to D, and I can just continue on. So now after this, shortest distance ij gives the shortest distance from I to j. So now all I need to do to update it to give the shortest time ij should be shortest time to get from I to j without leaving our house. Right, so shortest time is going to be equal to, should only have 1t, this with some slight adjustments. So shortest time, ij. Now, we have to be careful, because if, this actually should be shortest distance, sorry. So, we want to divide by horse info the speed was I1, yes. If, and let me just put this on a different line. So essentially what this is going to do is I'm storing for each ij the time it's going to take for us to get, using horse I, to get from I to j. Now, if we're only able to get there though if the shortest distance is less than or equal to the maximum distance that a horse can travel, right? So this is I0. Otherwise, the answer is -1. We can't go there in one step, right? So shortest is ij divided by horse info looks correct. So that's the shortest time. So now run Dijkstra's for each query is all we need to do to find the shortest path. So for query, or for Q1, Q2 in queries, run Dijkstra's from Q1 to Q2. And I think this is probably going to run over time for us in terms of like runtime, but we'll do it anyway. We'll see how we go. So I guess we can just copy paste a lot of this code, except rather than using source, I'm going to be using Q1. So wherever I see source, I'll place it there. I don't need to update the shortest distance. And as soon as all expanded Q2, right? So as soon as I find Q2 and I expand it, then that's also done. And let's just say save dist false times it, or -1. Right, so saved dist is going to be updated. Saved dist Q1, no, saved dist of v is d, sorry. Right, so then the answer to that query is just saved dist Q2. And I think that's good. So now I just need to print all of my answers nicely. So all answers I'll write as a string, and I'll just say all answers is all answers plus an empty string plus save distance for Q2. The output format wasn't exactly like that, was it? Oh no, it is. Okay. So if I put in all answers here, that seems to work. Okay, so let's just go through what we're doing in code here. We're starting with all our input, the adjacency list, the horse info, and the queries. The next thing we're going to do is compute that auxiliary graph, which is actually going to be shortest time, but we'll start off with shortest distance between each node. We run a Dijkstra's run from each source point to get all pair shortest paths. Then the shortest time is the shortest distance divided by the horse speed if the shortest distance is small enough, otherwise it's empty. And then we run Dijkstra's from our adjacency list, but I should be using, rather than edge here, I should be using shortest time, I've just noticed. Here. So now the distance is an actual time, and we're only moving to a different node if it's possible to, in that time span. And that's our answers. Okay, I think that is everything. So let's try the test cases. Let me just copy those down and we can run it. So there's a lot of info in these test cases, so it's going to be a bit hard to see what's going on. But let's see if we just get something reasonable. When I pass in 1.in, I'm getting a complaint. Why is t? Oh, okay, sorry. That should be int input there. And we're getting some complaints about list indexes being out of range. So while Q or expanded Q2. I see. So I believe if we just go back to the input statement, we're going to have an off by one error that I'm missing. So U, hang on. So the cities are numbered from 1 to n, but our indexing is from 0 to n minus 1. So all we need to do is for each of our queries, here, rather than just mapping it through integers, what we can actually do is map x to int of x minus 1, and that should work. No? Heap q dot heap pop q. So the popping doesn't work in line 72. That makes no sense, actually, because we're only doing it while q and not. Sorry. Okay, that looks better. So we've got 0.58, 1.2, and then 0.51, 8.01, 8.0. Let's double check what the solution says. Let's transition back. We can see we've got 0.58, which is what we had. We've got 1.2, and then 0.51, 8.01, 8.0. So it looks like our answer is correct. So let me just copy in the solution. Now, I don't think this will run within time because, or at least on the large data set, simply because we have 100 queries, which means 100 extra Dijkstra's runs, and 100 tests and 100 vertices. It might work, but I haven't quite thought about it yet. Let's submit and see what happens. Hopefully at least it's a TLE and not a WA, because I think what we're doing there looks correct. WA in the second case. That is surprising to see. So what's the difference between the first case and the second case? Let's see. So for test case 2, the only difference is we have more queries to answer, such as in case 3 here. And we also have each query isn't just from 1 to n, right? It starts off at different points. But I think it might just be that there is a slight issue with our algorithm, that the first test case is not big enough to spot. That's the only thing I can think of, because I don't see how having more queries that aren't just from 1 to n is going to break our algorithm. Let's double check. We'll have a read through. So Dijkstra's for each query for Q1, Q2, and queries. I'm going to start at Q1, search to Q2. Give you the save distance, which we're guaranteed always exists, and print that as my answer. The initial Dijkstra's run looks fine. Yeah, so I think we're making some minute problem here, but the algorithm seems to work fine given that we're getting AC. Yeah, okay. This isn't the outcome I was kind of hoping for, but it's what we need to get used to when you start doing contests. Sometimes you're not going to be able to complete all the problems, or they're just going to evade you for some reason, and I don't want this video to be 5 hours long, so I'm not going to try debugging these. What might actually be useful is I'll look through the solutions and we'll see if we missed anything in problems 2 and problems 3, and also if there's some things that we could improve as well, seeing as this is a run contest already, so we can see the analysis. Alright, let's check the analysis for problem 3. So we're using dynamic programming in the small data sets. But I think let's look at the large data set, because that's where we're going wrong, but it looks like we're doing a very similar thing. And I'll just take a drink quickly. So we've got G of the cities with distances between them, yes. Yes. The desired result is not the same as the units of the weights of the graph's edges, yes. So the obvious way to transform between the two is not a constant. Yes, so we made the same key insight that we need to construct a new graph with weights of time instead of distance. Then we can apply a shortest path algorithm and get what we want. Da 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 da. Yes, so it's defined by the single speed, h's speed, and that is just the distance between I and g and j divided by h's speed. So that's what we did. Yes, and the edges in our auxiliary graph represents a succession of a succession of edges in g dash. That is a succession of single horse paths in g, which is exactly what a solution looks like. Right, and since the limits are low enough, we need all shortest paths in g to construct g dash, and many shortest paths in g to answer many queries. So we can use Floyd-Warshall. I used multiple runs of Dijkstra's, but Floyd-Warshall would also work here. Yeah, and as I said, others will work too. To also check for the existence of paths, you can use the trick of setting weights to infinity rather than -1. Yes, but we just had an extra check whether our adjacency list was -1. Yep. So that seems fine. Oh, I think I found my bug actually. Because shortest distance, I'm just noticing. Yes, so shortest time I think is slightly off. And if shortest distance is -1, we also shouldn't be able to take it, right? So if shortest distance ij is equal to -1, i.e. we can't make it to that point, then the answer here should also be -1. Okay, let's submit that and see what we get. Maybe we'll do better. That is definitely a bug in our code, and I'm glad we spotted that. If I do get AC on that, I'll explain that further. Sorry about the noise, but yay, okay, we got it. So that was our bug. Let me go over what was happening there. So let me just get the notes up. So there's a section in our code where we go from this first graph to the auxiliary graph, and we go from distances to times, right? And essentially our graph in code looked like we've got these distances, right? So let's say I think we've got 4 here, we've got 5 here, we've got 6 here, we've got like 10 over here, and so on. But what we've also got is we've got like -1, for example, going this direction to show that there is no actual edge there. What we were doing before is we were saying that the distance from this edge is actually just -1 divided by S3, right? And that is the time it would take. It would take negative time to go from there to there, which doesn't make any sense, right? Whereas this would be perfectly reasonable to say that these take 4 on S1 and 10 on S2. So we just need to check whenever this is the case and turn that into a -1 instead, so that Dijkstra still works. Okay, but our algorithm worked, we got AC, that's awesome. Okay, let's also just have a quick look at problem 2 and see if we missed something, and then I'll probably end the video there for our solve. And let's again just go straight to the large data sets. Yep, so we made the same results that they did, and that as soon as we get a secondary color unicorn, they need to be surrounded by the same color, or the opposite color unicorn, so orange needs to be surrounded by blues, so on. They've also said that we need essentially to cover them on either side, so S+1 instances. If the secondary and its primary are the only 2 colors, then we can have equal numbers. So this was the case 4 in the test that we had to check for. Otherwise it's S+1. And they've made the same idea that we have, where we can put all of the same secondary colors of the same type together. And then, yeah, I guess something I kind of glossed over in my solution, but we do make use of, is that an RGRGR chain exactly acts like a single R, right? I guess that actually does make our solution a lot easier. now that I think about it, because now we can reduce from the secondary color solution to a single solution. Yes. Okay, so there is a way to significantly reduce the complexity of the problem, and that is just to turn all of your RGR chains together and clump them into a single color, right? You can consider them to be a single unicorn and then solve it that way. So essentially the solution would be that you solve it on the small data set with only simple unicorns by turning all of your RG chains and YV chains and BO chains into single unicorn colors, solving on the small case, and then replacing a particular red unicorn with the RG chain. Okay, that is a lot simpler than what we came up with, so I'm glad we looked at this solution. Okay, well, I'd say that's not too bad. We didn't quite get that second problem, but looking at the scoreboard, it seems that the third one was definitely the hardest. There was a lot of WAs on the second one, so we're not alone in that regard. But we did get the hardest problem pretty fast, I might add. So that's good to see. Cool. Okay, hopefully you tried a few of the problems as well. It'd be great if you could show me that you've done so I can see that it's actually working and this is worthwhile doing, but hopefully you enjoyed the explanations. I'm sorry I got a bit lost for words. I lost for explanations for problem 2, but hopefully the explanations for problem 1 and problem 3 were good enough. Anyway, cool. I'll probably do another one next week, but we'll see how we go. See ya.